Hello, good evening, good afternoon. Welcome to Codebase Alpha. This is episode 61, and this evening we're going to be looking at shaders, so GPU shaders using OpenGL. And we've got a special guest with us again this evening. We've got Mårten, also known as FuseLabel, in the chat. So he's going to help us kind of understand this kind of wonderful graphical world of OpenGL and shaders. So let's drop over into the pair programming area, and Mårten can introduce himself.
Yeah.
Hi, Mårten.
I'm gonna not getting feedback. Shut down the sound on your channel.
Right.
So yeah. Hello. I'm getting to be a little bit of a regular, almost. I feel like, and that's a nice feeling, I think.
Yes, I think we make a good double act. So I'm really pleased to have you back on here. And if we can, we'll probably schedule a lot more of these kind of dual streams in the future as well. So they seem to go down well. I
enjoy being here, and I hope that others enjoy sort of me being here and sort of distracting you from your sound.
Well, I think the sound project is on kind of almost permanent hiatus at the moment because of the problems I'm having with. The system I'm using is not playing well with OBS, so I think we're going to be that's going to be on hold until I solve that, or at least speak to the person who created that program and see if they can help me fix it. But yeah, it's a bit of a problem. It's a bit of a shame. Okay, then, so today we're going to be talking about shaders and all they can offer in terms of distracting us from proper work. So could you just tell us a bit more about what they are?
Well, yeah, so shaders, I guess. I mean, I'm not a super expert on this topic. I've never really been a game programmer. I kind of just been self-taught from, reading lit and experimenting a lot. But I've been thinking with graphics programming. I enjoy that. And basically, you can say that a shader, I think, is a small program that you can apply, that runs on the GPU, that can perform certain tasks, for instance, on transforming all the pixels in an image, sort of, applying some effects to it, or sort of, rotate all the vectors in a space, or do some tessellations and all these kind of things. But essentially, like if you take what I know best, and that is the fragment shader or the pixel shader, is that it's a small program that, given a texture coordinate or a coordinate, produces a color value.
Right.
It's a very simple model, I think, and it looks very much like a small console program, like that. Given an input coordinate, produces a color. And what's cool about it, one of the main things I think is cool about it, is that you can. One, it's massively parallel. The GPU has teraflops of capability. Even a bad laptop like mine has amazing amount of flops available, and you can sort of use that using the pixel shaders, and you can actually do a lot of useful stuff. But we're not going to do any useful stuff today, except learning a little bit about it. And yeah, so I think that's a really cool thing. So, 2 summers ago, I got into this what's called ray marching, which is about doing ray traces in pixel shaders. I've been thinking about that idea, but I never really did something about it. But then I found this site which I really enjoy, which is called Shader Toy, and there are like loads and loads of examples where people have implemented ray tracers real time in the browser, which I thought was a cool way to sort of do it and sort of share. You can do your own shaders and you can share it with people, and they can say, "Oh, that looks cool," or they'll most likely ignore it. But sometimes you manage to do something that people like. So maybe we start with that thing.
Yeah.
Looking at some cool shaders. So I have some links, and my hope is, after doing this work in this thing, is that it will be possible for you and the viewers to sort of read and understand the source code of these shaders, because they're all based on the same principle, which is called ray marching. So let's see if this thing works. I'm going to share. I'm going to copy a link. Where can I? Yeah,
you should be able to copy it straight into there. Yeah.
Yeah, but copy paste doesn't work, right? We discovered it, but let's try it. I can at least control it, right?
It's really interesting that doesn't work. So if you put it into CodeShare, then I'll pop it into the top.
Okay, yeah, that's a good idea. Let's do it. That CodeShare. So this is the first one I've had in mind. And you might have seen it before.
So today we're using Teams for this rather than Skype. So just so we're having a few kind of teething issues with the content sharing. But yeah, so this is something we saw perhaps on an earlier stream, maybe one of the T4 streams. It's
yes,
it's quite amazing, isn't it?
So what you're looking at is essentially a 3D fractal, which is produced, and then it's implemented a ray tracer that does shadowing and all these kind of effects on it. And all the source code you see for it is on the right side. So if I control the mouse cursor, I can control it down. So here's all the source code, and this thing is 160 lines code.
Yeah.
And that contains everything you see on the screen, basically. The ray tracer engine, the lighting engine, the sort of the shape of the object, it's all there, except this noise texture, which is really not necessary. So I think that's also something that amazed me with shaders. When I saw these things, I was blown away by the graphics. Like, how do you do 3D fractals? But also, how do you do it in so little code?
Yeah.
That kind of blew my mind. And there is something called 4K demo scene, where the idea is that you make executable that is just 4 kilobyte.
Right.
And they are almost all of them do is that they open a window, and then they draw 2 triangles in the window, so you form a square, and then they run a shader program that looks something like this, and you can get really amazing looking things in 4 kilobyte. But we can actually change the source code here. So let's see if I can find something to change. So we can reduce the number of iterations here and say, let's say 2, and we hopefully see that it's changed object. Okay, that's got quite uninteresting. But we can see at least something happened here.
Yeah. We got kind of just a skeleton of it there.
Yeah. So it's not really interesting, or we kind of lose something when doing that. But I mean, we can see it's live, and we can sort of change the source code. And that I think is also quite cool, that you can sort of see something that is kind of cool looking, and you can tinker around with it. This looks okay-ish. So and we can also change perhaps the scale. I don't know. Is it 2.5, 4 perhaps? See what happened? Yeah, something happened. And these kind of things. So that's cool, I think. This is a really cool site. And I found some other, believe are cool things to sort of, get started. And so let's see if I can find it. Another, which is really amazing, this is one of the first ones I saw. And that blew me in my, what blew me with this one actually, is that it was
that's the same one.
It was quite little code, also very well documented. Let's see, I don't think you got it there, right?
There we go. Hello? Yeah, there?
Yeah, sorry. I'm watching the screen. Oh, yeah. I actually watched the correct screen. Yeah, sorry. I'm watching it this one. So we see the Menge. This is a Menge cube. This is also a fractal. And this looks quite nice.
It's amazing.
And you have all the source code here, and you notice it's quite well documented.
Yeah.
And it's still around 300 lines of code. And this also runs really well on a mobile. So if you bring up your mobile cell phone and look at this thing, this kind of real-time ray tracing looks really smooth and nice on a cell phone, which I think is also quite cool. So you can make these kind of cool shader programs using that runs anywhere, kind of. Maybe even on my laptop. And the thing about this thing is a kind of maybe I mentioned it before. It's like all of these things builds on a technique called ray marching. And if I kind of want to sort of with this series or whatever we do here, sort of get across this thing that sort of that you can understand and see, and look at this program and say, okay, I understand how it's working in principle. I can make changes to it. There might be some tricks when it comes to lighting and sort of creating objects, but you understand the structure because 90% of the shaders on this site are all built up in the same way.
Right.
Ray mergers. And they're almost all based on work by one guy called IQ. So, and he has a certain naming convention, and most people have just copied the naming convention. So most of these things are very much alike. So this is cool looking. Let's see if I can find something else.
Okay.
Oh yeah, this might interest you. I think I shared it on your stream once, but I think it still is something good to sort of share. Let's see how it works. I shared it in code share here.
Yeah.
And now I'm going to watch the correct screen so I don't get confused.
Here we go. Oh, this is the sound one, yeah.
Yeah. So, and if you click here, you click sound. So you can actually make sound shapes. So this sound here contains the source code for building up music. And they have sort of how to make the drums by a combination of noise and
I think it's a bit loud with it.
Yeah, you could turn it on. But I mean, I just want to demonstrate that it's possible to also create music using shaders.
Yeah, that's really interesting for me. Yeah. Shame it was a bit loud then, because I think it drowned everything out, but you get the idea.
Yeah, you get the idea. Oh yeah, this is... see if I can find someone here. Oh yeah, I'm gonna kind of show you. You can also make 2D shaders, and that's kind of where I think we might start with the shaders today, because sort of 3D shaders, as cool as they are, I share something new here in CodeShare.
Yeah.
And that's kind of where I started. I think it can be quite hard to understand. If you start with 2D shaders, you can get the language down, and we can start talk about some concepts that are common for some effects we're going to do in 2D, and that it's easier to understand the 3D shaders.
Yeah. I think it start with something that's a lot easier to grasp. I think if you find thinking in 3D can be quite hard. So
yeah. But this is, by the way, the reason I want to show you is this is the inspiration for, or this what I based the Electric Elf on.
Yeah, you can recognise the idea.
So it's
Electric Elf's way cooler.
Yeah, I'm quite satisfied how it came out. I looked at this code, and I think I added a little bit of personal touch to it. And of course the Electric Elf or the Elf logo, and that's there you have it, kind of your Electric Elf thing. Maybe I should show you the best shade I've done myself.
Yes.
Just for the fun of it, which I'm most proud of. So I'm just gonna find it. I didn't think that I had, and I got some positive comments on that as well. So that's always cool when people are seeing it and they say it. So I'll just find a link. Sorry.
I'll just show Electric Elf if people haven't seen it.
Oh yeah.
There's the Electric Elf.
Can never have too much of that.
Yeah. So you can see the similarity there. And the other one we've got is Infinite Elves, or the hyperspatial hype, which you've probably seen before, which is this one. There's another one of Mårten's with our elf alien friend in it.
Yeah, and this hyperspace thing. We call it, this is actually what you're looking at is a Julia fractal that we applied texture mapping to. So if you know the Julia fractal, we can actually do this Mandelbrot and Julia fractals real time, and then we texture map it to sort of give this weird thing going on, which is and you can actually see the Julia shape occasionally. So surprisingly simple, and that's also what I like with shaders, is that you can make things that are quite cool looking, and it's not that hard. It's a little bit of effort, but usually you can program something that is like 200 to 300 lines of code. Did I get you the right one here, by the way?
I think so.
Yes. You can turn off the noise here, sound here, noise.
Where's the sound control?
Oh, that's a good question. I think there is this here.
Nice.
Yeah. So this is a shader that supports transparency and uses ray marching. And then I have different kind of shapes here that I go between. I think it turned out pretty good. And I also implemented something that's called Beer's law. And maybe you see it, that the further the ray travels through the glass, the more it loses, it gets absorbed in the material, kind of. But then the blue stuff in the middle, I did the reverse thing. I actually made it that illuminates the ray, so it gets lighter when it goes through that. I thought it created quite nice effect. And some bubbles.
It's like a 1980s lava lamp, that is, isn't it?
Kind of. And so on and so forth. So this is one I'm pretty satisfied with this thing. I think it turned out. It's not super complicated, but I thought I found some pretty interesting shapes, and I found some nice music to add to it. Because you can add SoundCloud music. Obviously, I'm not able to do music myself. Oh, by the way, this is a Mandelbrot fractal.
Oh, right.
And which has a pretty interesting surface, and then we can see that it's still a sphere in the middle, but because the refraction of the glass, it gets distorted in a, I think, cool way.
Very good.
So, and hopefully, right, this is where we want to end up.
Absolutely, yeah.
So shall we start writing some code?
Let's write some code.
And let's see if we can get there.
So in order to write our code, we're going to use Kodelife, which is on this site here, hexler.net. Actually, Hexler is they followed the stream, so if anyone from Hexler is actually in chat, then welcome. So this is the program we're going to use. There's versions for Windows, Mac, and Linux. So if you're on Windows like me, just download this, install it, and away you go.
Yeah, so this I started using writing in Shader. So Shader was quite good, but I think that this is a much better experience because you can work interactively in it and sort of make changes, and it's recompiled immediately, which is, you can see the feedback on things happens at once, and I think that's very good. It's a very good idea, I think, and this is actually coming to this idea that, what is this called? Like, you want real-time feedback on programming. Yeah. Some people talk about this as a paradigm shift, and this is actually available here. So if I take and change a little bit of the source code and make this a little bit more boring, I'm going to remove some code here, and now it goes white.
Yeah.
So that was maybe not so interesting, but that's something to start about. What's cool, it gets recompiled as I'm writing, and now it goes, oh, gray, amazing, right?
Yeah.
So how do you read this program, right? For someone that has never seen it, and if you know C#, or if you know Java, or if you know C++, you think of it like a very dumbed down version of that. It's not really fair because it's also quite smart, but remove all objects, remove all the allocation of memory. We don't do that here.
That's good.
And don't do recursion.
Right.
And it's basically C in many ways, except we don't allocate memory and we don't do any recursion. Hello, Stoolpenner.
Hi, Stoolpenner. Welcome to the stream. Good to see you.
So if you're able to sort of, understand if you know C#, I think you are actually in pretty good shape to understand this as well. What it does have, which is quite smart, is these vector types. And if you're working with shaders, a little bit of linear algebra it will help you. So not very advanced linear algebra, quite basic level, but if this is a floating point, and this is a single number, which is a floating point, we know that. What is this thing? vec2? Well, that's two floating points. It's a pair of it, kind of, or a vector. And there's also types called vec3 that contains 3 values, and then it's called vec4. And it's very common with linear algebra that you are operating on these things called vectors. And you can think about it. Sometimes a vector is and the vector is used to represent many things. It's used to represent a point. We get an input here, the texture coordinate. That's a point in the texture, like the pixel coordinate.
It's an xy pair, isn't it? That.
Yeah, and then we produce a vec4, which is the final color. And the first one is we can make this a little bit more interesting, right? So I'm gonna do it like that. Gonna write it like that. So now I'm initializing this vec4 using 4 numbers. The first one is then is in this case means it's red, it's green, it's blue, and it's alpha, which is not really used here.
So the alpha is like the opacity, isn't it?
Yes. So it could be used downstream, but in this case we don't really. It doesn't matter if I make it 1 or 0, but it could be in other situations. So a vector is also used to represent colors, but it's basically as a tuple, like C# tuples, a collection of floating points. And what's quite cool with, which I want to mention, because we're going to do that kind of things, is I can write stuff like this: xy equals u. Oh, sorry. Yeah. uv.xy.
Yeah.
And now I can do it like this, for example. And then that's not so strange, but I can also type like this, which means I can select the xy coordinate and store them here. I can also flip them like this.
Yeah.
If I just type this is a floating point. And if I type like this becomes a vec3. So this is a quite cool and powerful way, I think, to sort of work with vectors. It's very useful in this case. You can create some quite powerful operations. But you should read it like, I think you can read it like Swizzle. Yeah, that's what's called.
Swizzle, yeah, that's right.
UV, select X dimension and the Y dimension, and that is the result. And if you type it like this, select the X dimension, Y dimensions, X dimension again, and then it's now a vec3. So this is used a lot. So that I think is maybe a little bit different.
Yeah, if we need to go into any linear algebra or vector stuff, then I can do a few little kind of drawings and things and explain that. But until we come across it, we'll leave that out of it.
Yeah, and to be honest, I don't think it's going to be that much. I'm confused. I'm probably struggling more with the keyboard than anything.
Yeah. So Mårten's having to use a British keyboard layout to.
Maybe we have some drawings. We can make some drawings that could be useful here, actually, when I think about it. So length is not so hard, right? That's the length of a vector, or if you have a position, that is the distance of the position from origo, the 0 point. So I think most people have a little bit understanding of that thing. I hope, or I guess, length.
Yeah, length of the vector, length of the arrow.
A very common operation in this world is. Oh boy, look at you got a subscriber.
Cool, Penna. Thank you very much for the subscription. That's absolutely awesome. So thank you so much, and welcome, Dragoneye. Normally, still, Penna, I would welcome your subscription with some hyperspatial height, but that's over on the other scene. But we've already seen hyperspatial height. What we'll do is I'll get Alf to give you a nice salute there, and then I'll go back to thinking about this code.
So something that is quite common that we might do sometimes is what's called dot product.
Yeah.
Which is a little bit different. And the dot product is actually, it has a quite it's a very useful thing, and one of the things it's very useful for is to determine the angle between two vectors, if that makes sense. So if the let's see if I can rewrite it in some clever
Shall
way.
I try to? I'll tell you what. I'll go over. If you just let me go over to Notepad here. I'll just do a quick drawing. So yeah. So dot product. We've got a couple of vectors. Let's see if we can write something in this pen. Oops, not gonna. Yeah, select that. So yeah. So we've got x and y, the vector. Get rid of that. And we've got, I don't know, a and b as a vector. And we're going to do a dot product. So these are two vectors. The result of a dot product is going to be a scalar number. It's just an ordinary number. So it's going to be, basically, we're going to take x times a plus y times b. And you can see if these are floating point numbers here, this is going to be a single floating point number. So that's basically what your dot product is. Okay, back to you.
Yeah, so I wrote something in the code share. If you switch that thing,
Can have a look.
Which maybe can help.
There we go.
So
yeah.
The dot product, the result of the dot product is the same as the length of the first vector multiplied by the length of the second vector, and that becomes a cosinus multiplied by the cosinus of the angle. So if you want to know the angle between two vectors, we can use the dot product to sort of, instead of saying this thing here, we should yeah. I'm watching your screen and writing it. That does almost worked. The latency was actually quite good. So if you say that the angle would then be equal to the dot product divided by this length here, and then we take the inverse cosine function, which is also available, by the way, in it's called ACOS, I believe.
Arcsine, yeah, arccosine. Yeah.
So sometimes we need to know the angle between these things, and then we take the dot product between these two vectors, we divide by the length of the multiplied by the vectors, and then we get the angle, which we can use stuff. So this is sometimes very useful. Now you got another subscriber.
Yeah, it was a follower. So Gabor, thank you very much. Thank you very much for that follow, boosting us on towards our target. So one of the interesting properties of this this equation that Mårten's put there is if the dot product is 0, then it must mean that the two vectors are perpendicular to one another.
Yes. And later on, when we talk about ray tracing, this dot product we will use to determine the shading of the surface, because there is I forgot the law, but there's a law that says that how illuminated the surface is the dot product between the normal of the surface and the direction to the light source.
Right.
So what we do then is we find a point on the surface and we compute the normal, and the normal is something that how do you describe the normal? It's points perpendicular.
That's right.
Perpendicular to the surface, so it points outwards, like you draw. I don't know. But you take the normal, and then you take the dot product to the direction to the light source, and then you can compute the color, how much white or how black the color should be, and that looks quite nice actually. So that's something very common. And another quite common operations is something called the cross product. I'm going to write that in this thing here.
You're writing that?
Well, I write that in here in here. So we're not going to, the cross product we don't use so much, but I think it's worth mentioning because it kind of complements the dot product. Oh yeah, it's hard. It's hard work.
Yeah, I bet. Yeah, keep you on your toes.
Okay, it seems it cannot make a cross product from.
Yeah, I think you need a vec 3, don't you, for a cross product?
A vec 3, yes. It kind of makes sense to be a cross product.
Yeah.
So this does make sense, but the idea here is that the cross product takes two three-dimensional vectors, and if you think about geometrically, if you have two three-dimensional vectors, if you have two vectors in space, like the points, in order you can create another vector that is perpendicular to both of them.
Yeah, back in your maths classes, you might have come across the right-hand rule.
Yes.
So this is where you do this with your right hand, and is the perpendicular vector.
Yes. That's right. So, and that is what the cross product does. So that's useful when we will create the three-dimensional space we're going to go through. Then we can compute. What we do is we compute a direction from the eye towards the point we're gonna ray trace.
Yeah.
And then we have a direction what it means to be up. But in order for it to be a three-dimensional room, we need a third vector. But then we can create a third-dimensional vector using these two vectors, and then we get the third one.
I've got before you carry on. I'll just go back to you. I'll draw the cross product on here as well, because there's an I think it's interesting anyway. So let's see if I can draw the cross product. So if we have a vector a, if that's the x value, a, y, a, z, that would be equal to, I don't know, b, x, b, y, b, z.
Mm-hmm.
And then the cross product with c, dx, dy, dz. Okay, so that is actually equal to, so my brackets have gone really wonky, so that would be equal to b, y, c, z minus b, z, c, y.
Yeah.
And then the next one is b, z, dx minus bx, cz. And then bx, cy minus by, dx. And the interesting fact, the fact you can bore people out with, if you take the first row, you see you've got an x here, and a y, and a z, and a z, and a y.
Yep.
So that's x, y, z, z, y. And if you're watching my streams on the old school text adventure, you'll realise that one of the magic words in the text adventure is x, y, z, z, y. And this is where it comes from. It comes from a mnemonic to work out the cross product. So the first row is always x, y, z, z, y, and then you just rotate the suffixes around the little I can't remember what you call them off the top of my head, but the little suffixes here, you just rotate them around. So x, y, z, z, y comes from linear algebra. So the end of ridiculous fact number one. But I like that.
But I mean, yeah, you can just. I mean, there's probably several clever ways to do it, but you could, in order to sort of compute that thing, you can actually put up an equation system where A has to be perpendicular to both B and C vectors, and you solve that. Equation system, and then you get these things. So impressive, showing off there. Mad skills. But the thing about this, when we talk about ray tracers, is this is actually kind of what you need to build these ray tracers we saw before. The math doesn't get worse than this, which I think is pretty interesting. So if you can grasp sort of linear vector addition, length, dot, and cross, you have the tools, the mathematical tools to understand it. Of course, then there are tricks and there are some ways to apply these things that can sort of be hard to understand sometimes. But the fundamental, you don't need more than this from the linear algebra. So you need to basically learn three new operations: length, dot, and cross.
Yeah. So I've got a book this thick. It's Strang's book on linear algebra, and basically this is all covered in the first chapter. So you can stop reading your textbook after that, and you've got everything you need, all the tools you need.
Yes. So, but today, right? I thought I thought we can sort of, start writing a 2D shader, because I think there are because ray traces might be the final goal, but what I also want to introduce today is something called distance fields. And a distance fields is a function that gives the distance to the object.
Right.
So, and that's actually all of these ray tracers that we looked at use this thing, because they had a special mathematical function, like the first fractal, that you could pass in a 3-dimensional coordinate, and it told you how far is it to the object. It doesn't tell you how far is the closest point to the object.
Right.
It didn't tell you what direction. It didn't tell anything like that. It just told you how far are you from the object. And these functions, I think, is good to have an understanding of how they work and what you can do with them. And you can get a good understanding for that in 2D, because it's much easier to visualize them in 2D.
Yeah.
And then I hope that when we go 3D, when it's much harder to visualize it, it requires much more sort of mental exhaustion to sort of do it.
Yeah.
Maybe you can go back and sort of try to visualize it in 2D, because here it's much easier. 2D plane is easier to visualize than 3D.
Definitely.
3D. So if you look back at the program here, let's start by sort of drawing a circle.
Okay.
Using a distance field function. And how would we go on and do that? So, I'm going to write some code here.
Okay.
So the distance to the circle. So what we get here, the input point, the UV is the input point, and that is, it's -1 in this corner, it's +1 in this corner, and it's 0 in the middle.
Right. That's right. All the coordinates are normalized, aren't they? They're all between +1 and -1. It's a bit like music, audio kind of coding. That it's everything's normalized between +1 and -1.
It's nice when it is that way. So for what we're going to do now to draw a circle is we're going to compute for each point how far this point is from the circle. And when it's very near, we're going to paint that pixel as white. And when it's not very near, we're going to paint it as black.
Right.
So what is the circle? Well, then we take the length of the UV. It's very, very hard for me, this thing.
Don't worry.
It's like using Jira at work. That's always where I'm struggling.
Yeah, Jira's like that, yeah.
Yeah. So what we do here is D will be 0 when UV is at a distance of 0.5 from Origo, and Origo is in the middle. So around this, if you can see my mouse cursor,
yeah,
around this thing here, the pixel, the distance should be close to 0. Around here, it will be a positive value, and inside here, it will be a negative value.
Okay.
Indicating we are inside the object. So, and I'm gonna rewrite the program a little bit here. And there are different ways of doing it, but I like the distance functions because it turns out you can implement so many nice things with them, and operations that are hard when you don't use distance functions are simple, very, very simple, and some others are hard, of course.
Right. Okay. Well, it's fairly simple. We can see that it's we're going to have a circle of a radius 0.5, I guess, at this point.
That is the goal.
Yeah.
I also have a little bit of lag when I'm writing, so that's why I'm struggling a little bit here. So there. So what I'm just going to do here, and I'm going to show you another cool feature of GLSL. I thought I'm going to show you that at least.
Mm-hmm.
Call is now this is a 3-dimensional vector. So take the 3-dimensional vector and append.
Yeah, that's really cool.
alpha. That's also pretty cool stuff you can do with this. So now the purpose is to sort of make col white when d is close to 0. How would you write that code? An if statement, right?
Yeah.
So let's do. Now I'm going to leave it to you. Sort of, I've done my part.
Okay. So we could say, like, I don't know, if
yeah, if d is less than 0, for instance, like inside the circle, then we set it to white.
Something like that.
Yes.
We got the ellipse. That's interesting.
Oh yeah. Okay. It's because we have. I'm going to write you a short piece of code here, which is you just learn to write by heart after a while, and you don't really understand anymore how it works. If I just can get it. Boy, where is the multiplication sign?
Yeah, I'll do it for you.
Yeah.
There you go.
No, confused. I need a division.
What do you want?
Divide by. Like I said, I'm not used to the British keyboard.
Yeah.
And I don't have it on my keyboard, so I don't know. I have to guess.
That's an assignment. Yes, still pen. I get work out on these streams.
Yeah. Now, of course, this is. I did it wrong. It looked kind of cool,
though. It does look good. Yes, it's an hourglass shape now.
Yeah, but what I wanted to write is this thing here. No, I tried. Does that work? No.
What do you want me to do?
Stop something. Type instead of UVX, type resolution.
Yeah.
So what we're gonna do is we're gonna just adjust the resolution, and you can't play the keyboard. There
we go.
There we go. Now we have it. So we normalize the X vector.
Yeah, it's because our obviously our window is not square.
Yeah, but maybe we should talk a little bit about the uniforms up here.
Yes. What are those?
Yeah. So ignoring what uniform means, these are the input parameters from the surrounding environment. So, for instance, resolution is set by Kodelife, and we can actually change the resolution if you here. So if you would change this to something else, I don't know, that would change the resolution input. If we start a time here, like we start running this thing here, we don't use the time yet, but if you start a time here, the time parameter starts ticking. So this is kind of the input variables. And oops, sorry.
Sure, that's me. I've changed the size.
Yeah, we're doing two things then. Let's change it back to the normal one.
There we go.
Okay.
Don't know what's gone wrong there. Hang on, let's have a look.
Well, it was working. Let's try something.
Yeah, just make a change.
You see, we get the white line there. Is it? Okay.
Is it crashed, perhaps?
Or is it that it's? Let copy paste this text we have here, and we just create a new product.
Yeah.
You need all of the text. You need to the top.
I thought I did did I not copy it to the top? I thought I did. Obviously not.
Okay, but it doesn't matter. Okay, a new one again. And you replace the main method. And then we remove some extra stuff we don't need anymore.
Yeah. so we don't need this. Don't think we need spectrum.
No. And now it's white because I made everything white. So let's scroll to the bottom, and you can start putting color there instead of in front of
There we go. We're back.
And yeah. So these are basic input variables. Too white.
Yeah, you're blind. Yeah.
Time is ticking. We can turn it off.
Yeah.
So uniform is set by the environment outside, and they are kind of constant. It actually tells the shader that these values are the same for every shader unit. I see what it means too, but too many colors, yeah. So these values are the same for every shader unit. So that means these are actually constants that are global for each unit. Whereas the input arguments to this fragment shader is the texture coordinate, the normal of the point, we don't have it here, and the position of the point in space. And what we're going to produce is the output value. This is the output value. So you can think of this as a console program that as an input kind of argument, given these things, and then we are writing to stand it out. Not really, but kind of a fragment color. And, we don't see it, but this is a massively parallel program. This program here we are writing is actually applied for each pixel. So each pixel, this gets executed once.
That's right. So this is operating on individual pixels. That's the kind of amazing thing. It's like each pixel on this 1920 by 1080 window that we're working in is having this function applied to it once.
60 frames per second.
Yeah.
And it turns out that we can do a lot of things inside here. But already in here we are actually doing quite a few floating point operations for this very simple program. But the GPU is so powerful, so this is no problem. But let's make this. Let's change it a little bit, and I'm going to write a suggestion here. So I changed this to abs. I thought I did at least.
All right, we've got a torus now. Right?
So now I say when the distance abs makes it positive, right?
Mm-hmm.
Absolute value. So when this distance is less than a certain value, I just picked one that sort of fit screen. We see a circle. So here's the inside, and here's the outside. So one thing that is actually quite useful when trying to understand, because what we actually are looking at is a distance field, but we only see the points that are closer to the circle.
Yeah.
But in order to sort of visualize the distance field here and sort of see what we're doing, we should implement a function that shows the different colors depending on how far the distance.
Yeah.
And one way to do it is, we have this the D value here. So we have the D, and then we're gonna, I don't know what we're gonna call it. I'm gonna call it MD because I can't come up with something good. and what I'm gonna do with the modulus operation. This is the same as modulus, but this is how you do it in the shaders. You type mod, and I don't know, 0.5 perhaps.
Okay.
Or maybe 2. I'm just picking a number. And now I'm going to take this here. So what this means is that the modulus value means that MD will. You have to help me.
Okay.
Copy paste this if thing here.
Okay. It's interesting.
I think it was the wrong thing here. No, I think you removed the wrong one.
That's okay.
I wonder if we messed this one up. Can I look around in the code?
Yeah.
Can you press undo a few times? I think it looks like we have something strange going on here. So we get back to something runnable. Oh boy, more than a few times. Ah, I see.
There we go. We're back.
Okay, we're back. Okay, I can try.
I'll do it, don't worry.
Okay.
There we go. I don't know what happened before, but there we are.
No, let's ignore that. It never happened. So I typed MD here. So what we now see, we have we actually see the distance field here.
Yeah.
And let's make this a little bit more thick. So what we're seeing, what we took the distance here and made the modulus, so it's actually repeating. So now we see so at this point we are at the distance 0.1 from the sphere circle, and here is 0.2, 0.3, because at each step here it's increased by 0.1. This is actually very useful, but I also think it helps if we get different colors, right?
Yeah.
So what you can do is you change the if statement. So if it's how do we do it now? I'm confused. Yes. So if we're inside the object, it should be a different color than if we are outside the object, right? So inside here, this if statement, you can sort of write another if statement that's saying if d is less than 0, then we use a different color. If d is, and otherwise we use another color. So we can sort of see the difference between these things. Yeah, now we also see the inside. So that's cool. Else. And you see it updates immediately, so you get this feedback, which I think is nice. At once.
I don't know what do you want to do.
Yeah, let me. We can just pick some gross colors to start with, and then we can sort of tweak it. So I'm gonna. Yeah, that's okay. And then I can take this one. Can I borrow the mouse cursor? Yes.
There we go. Yeah.
So now the green is outside, and the red is inside, right?
Yeah.
So now it's easy to understand how the distance feels. But we also, I think, something that can help even further is we make sure that the further we are from the distance, sort of, it goes to black. Right?
Yeah. Okay.
So, and one way to do it is actually very, very simple. Hopefully I do it correctly as well. So instead of taking the modulus, now you have to help me. Okay, this is the hard part.
What do you want to
do? A division character.
There you go.
And you divide by 0.1. So this is the period kind of what we're getting. So if you instead then divide by and take the absolute value of this as well, when I think about it. Okay. And now you divide the color here, the red color and the green color by ND. Because at the first circle it will be 1, at the second circle it will be 2 and 3.
Yeah.
So now we got
so we're already getting some really interesting effects, aren't we? Just some few lines of code like that.
Yeah, it's quite powerful technique when this thing is applied to every pixel. Certain operations.
Sorry. I was trying to correct that.
You tried to help me, right?
I was trying to help you out there, yeah.
Okay, I was trying to make it.
I thought it was like live code, and this is not live share. This is actually just sharing the screen, so we can't both type at the same time.
But the cool thing about this thing is actually this is a generic we create now a generic way to visualize distance fields. So now we're seeing a distance field to a sphere. And we can actually think a little bit with this sphere here now and say, well, what if we want the sphere to sort of move a little bit to the side? See if I can.
Right, yeah.
Like that. So, like so. And now we can actually do something that I sometimes do just to sort of see what happens. It's like, can you give me a multiplication sign? And I go see sine time.
And we got an oscillation. Wonderful.
Yes. And we can even make this move in a circle by take 0.2 time cosine if you do that. So in the y-axis you type 0.2 times cosine of time.
Baguetza, welcome to the stream. Good to see you. So you made your own shader effect editor. This is Kodelife that we're playing with today.
It's very nice.
So yeah, so it's hexler.com is the website. I'll just show the website if you're interested in getting a copy of it. My mouse has vanished. Anyway, carry on, Morten.
Yeah, so instead of 0, you type 0.2 times cosine.
No, my mouse is back.
No, not there. Instead of the y-axis.
0.2. Oh, here, right. Here.
We want to move it in a circle.
There we go.
Amazing. But this is still a distance field. We are just moving this, distance field together. And now we have this work. Now I'm going to stop the time here. Something that fascinated me, that really got me into this thing was, do you know the Boolean operations of shapes? Like if you take, the Boolean operations of true and false, we all know that kind of things. But there are like geometric versions of Boolean operations for shapes as well. And that is, if you take the union, you get a shape that is constructed by these two objects merging into each other.
That's right, yeah.
And if you take the intersection, then you get the volume or the space where they both exist, kind of.
Yeah.
And then you can take the exclusion, and that is creating the shape where you removed the other part. And when I started with triangles. I kind of come from the assembly time, like assembly programming on Atari Amiga. So I tend to think, we didn't do triangles, but I tend to think in terms of triangles and objects and like that.
Yeah.
And implementing Boolean algebra for triangles is a pain. It's so hard. It's so difficult. But then I learned how to do Boolean algebra. And we're going to do it in 2D, but the exact same things work in 3D if you use distance function. It's just as simple. And for me, this was just mind-blowing how simple it was. So I'm not sure if you're going to get mind-blown, but I was blown apart by how. So I thought this has to be good. If this is that is so hard, is so simple, this has to be good stuff. So what I'm going to do now is instead we're going to do the union here of two circles. At least I thought so. So I'm going to do the circle one. That's the distance one. Okay, now you have to help me.
Okay.
Maybe I can do it myself. Let's see if I can do it myself. I'm grown up now. Copy. My sister got angry when Use
He
the
did it. He did it.
use the keyboard. This works. So what? So and then let me do this thing. Yeah. So I take float d equals d1. That's the first circle. And this is the second circle. Now, I want to show the object that is the combination of these two. How do we do that? Like, how do we take the union of these two objects?
Is there a union function we can use?
Kind of.
Yeah, there we go, yeah.
So this is just the minimum function. It returns the minimum distance.
Okay, right, yeah.
So when we are here, the minimum distance to the first sphere is exactly here. But when we're over here, the minimum distance is here.
There, yeah.
So I was, maybe you're not as blown away as I was, but I was blown away how something this usually is very complex can be so simple. Now, let's say we want to take the intersection. We want to take the part here where these two objects are intersected. What do we do then?
Max, yeah, there you go.
Then we take the max function. And we get the intersection of these two objects. Like so.
You got Sauron's eye.
So how do we do the exclusion? How do we sort of subtract the other object? And then what we actually do is we're reverting the distance, one of the distance functions, so we get the inversion. Yeah. And then we do the intersection of these two. Now we get that. So I thought this was so cool when I first saw it, because this is creating these kind of shapes. I mean, imagine you were drawing triangles on these things, and trying to create these objects.
I wouldn't know where to start to actually draw that out. So all you've done is use the distance.
Yes.
Distance from two points.
Yes.
Yeah.
And what turns out is many of these shapes we saw and looked at, and what we're going to create using the combination. Very good Dragon Eye. I was also mind blown. Good that someone else is sort of, what we're going to do here when we create this distance function, we can create very complex objects using these things. And when we go to 3D, so the Mandelbrot picture is actually a combination of doing intersection and unions of simple objects to sort of create something that looks extremely complex and is extremely complex, but we do it using simple and intersection and union operations over and over again.
Yeah. And it's that repetitive, isn't it? It's the repeating it over and over again and it builds up the complexity. Yeah.
Yeah. So let's see if we can make this. We can make this a little bit of add a little bit of animation to this. So let's take the scene time. Goes. Oh, that was hard. What I thought.
You got the multiplication sign up there.
Yeah, now I got it, but I didn't want it. So, and it's complaining about missed the parentheses somewhere, right? Did I miss it here?
It looks all right. There we go.
And we should make it a little bit less. Maybe, yeah. So let me start the animation. So what we're seeing now is just we have an object, and we're just taking the intersection of the big sphere. And if we do it like that, it looks different still.
Even better.
So, I mean,
I can see why you can sit here for hours and and play around with this, it's just like mesmerizing, isn't it?
Yeah, it's a little bit mesmerizing when you look at it. And using this kind of distance, using the distance field, it actually looks already, I wouldn't say super cool, but it looks a little bit cool at least.
Cool. It's pretty cool.
And concerning the amount of code, yes, exactly right. Med get stub is like that is definitely something that's used in ray marching.
We hope to get to ray marching and 3D work at some point in a future stream, but we're starting off with just 2D to get our minds in line with the kind of concepts of these distance fields.
But I also think that this distance field, we're going to talk about distance fields when we go into ray tracing, but there is much more harder to see the distance field, how it works. In a 2D, we can actually see the full plane and sort of understand, at least I think, using this simple math, simple how the distance field changes over the distance, and sort of understand it.
Yeah, it's quite clear, but even just with that simple concept, to be able to get such a, it's a really interesting looking animation. It's so simply. We're less than 60 lines of code still.
Yes. So where do you want to go next? Shall we make a cube? Not cube, I think 3D. Shall we go create a box, or what do you want to do?
Yeah, square would be good.
So what you can do now, as good programmers, maybe you should make a circle function. So you can extract this circle part, right, into a function. Just the length. It's just simple, because then we make a box function, and then it's sort of, we make a box function, we make a circle function. We can create this kind of, helper function that we can reuse over and over again. So if you can start by just creating a function and call it circle.
What's the output? Vec2, is it?
This is float, because it's the distance. This is going to return the distance to the circle.
Okay. The circle.
Yeah. As an input, it takes a vec2, which is the position of the pixel, and also it takes the radius of the circle, right? It's okay, at least I think it starts. And what you return here is just the length, basically what we wrote below, the length pos minus the radius, not inside, outside the parentheses. And then you refactor, instead of using the length function, you use the circle function.
Down here.
And you need to move the 0.5 into the parentheses now. Yeah, remove the parentheses next to a comma.
Yeah.
And you add the parentheses end, right? Yeah. And then you do the same thing for the line under.
Still going.
Okay. So how do we do a box? Because if you can do a box, then we can sort of combine we can sort of combine the shape of a sphere. So I say sphere, I always think 3D. A circle and a box. There's actually a cheat to kind of make a round box. So I can write a function to make a round box just for the fun of it. And that's actually I sometimes like this because Christ. So because you can kind of make a round box as a sphere, but you sort of you don't use the length function. You actually I'm going to show you. This is
show me. Yeah.
to pos. This is, I actually use this very simple function quite often when I do it, because I kind of like how it looks. And it also has when you do 3D, very sharp corners can be hard to make look good. Now we need the curl brackets.
Yeah,
no, I probably can find them. No, not there.
I'll do them for you. You got them. You got them. We'll have you a British keyboard user in no time.
Yes. So what I'm going to do now is I'm going to do yes, pos. See if I can do this correctly. Ah, Christ.
What function do you want? Okay.
I'm after this elusive. So what this means is I'm just multiplying x times y times these things. So this is just I'm multiplying x with x and y with y, kind of. So I'm if you get that. So I multiply x by x. So this is power by 2. I was power by 4, kind of.
Okay.
And I'm gonna compute the d8, the distance power by 8, by going dot, and hopefully I get this right. Return pow d8 by divide by cube square, kind of.
There you go.
Hopefully I didn't mess this up. And then oh boy, I'll probably mess this up somehow. Wow.
Interesting though.
We got something. Let's see how it looks. It looks quite funny.
Oh, it's a round cornered box, all right.
Oh yeah. No. So let's see what I made mistake here, right?
Ah, the radius, yeah.
There we go.
Yeah.
A very nice rounded box. But the basic idea here is we are using Pythagoras for length, right?
Yeah.
And that is x power by 2, right? Is that how you say it in English?
Yeah. X squared, yeah.
X by 2 plus y by 2 and square root. But in here, instead of taking power by 2, we do power by 8, x power by 8, y power by 8, and then we do the 8th square root.
Yeah, the 8th root, yeah.
And that gives not a circle, but that gives kind of a box with round corners, which is sometimes useful.
It's a useful thing to know, yeah.
So, and this tends to, when I do 3D, this tends to look better usually. So now we can put these two together.
Mm-hmm.
And once again, very simple to do this intersection, all these kind of things.
Yeah.
Because we created this. What's cool about this is, at least I think, we created this generic way to visualize the distance function. And now we just compute the distance to round box and compute the distance to circle, and the union operation worked. Dragon, I had a question here on. Okay, stop it. Oh, okay. Can I approve it? Yes, I approve it. Boy, I'm a moderator. I can add it to my resume, Twitch moderator. So, Dragon, I had this question here. Doesn't pos equal pos get overwritten the second time? No, we take the pos value gets overwritten here at line 32, the input pos. But then we take the input pos again and overwrite it again. So we could create this local variable and sort of make this vec vec2 pos1 and pos2, but this is sort of a way to sort of avoid doing that. So we're chaining them in place, if that makes sense. So, and then in the end, and the dot product kind of multiplies them again and sort of add it together, so that we get kind of the 8th power here.
Yes, remember with the dot product, you're getting a scalar. You get a scalar value out of that, so it's a number at that point, rather than being a vector. You say dot product.
Do you want to try to do the box?
Can do.
The box with sharp corners.
Okay, we can do, yeah.
Yeah. So let's make a function that has the right signature, and you call it float d box, perhaps.
And we want the vec2 pos again.
Yes.
Do we want a radius?
No, a box doesn't really have radius.
No, it has a length of some kind, don't we?
Width and a height, right?
Sorry?
So it has a width and a height.
Yeah.
So we should take a vector.
Oh, a vector, yeah. Vector 2, yeah.
Which we call the dimension. Size is fine. Size is fine. And return 0 for now. And then we need to think a little bit what it, because this is not obvious how to do this function.
No.
But I think by doing it, we can learn some cool tricks by doing so that we can apply later on. So how do we do that thing? Well, I think we can start by creating, by doing a plane, if that makes sense, where we have an upper and lower part. So the upper part is outside the plane and the inner part is inside this plane. So we have a plane that sort of, covers the whole screen. So I'm going to write something here.
Okay.
I'm going to say float distance x from this plane is equal to size, no, pos x, yes, minus.
Okay, size x, yeah.
Size x. And we return that thing. The x. This is not a box, right? But we start with that thing and we see how it looks. And then we, oops, sorry. Also, tell me if I go too slow, too fast, because I don't.
No, I think we're pacing it right. So if we got any comments on the pace in chat, are we going too fast or too slow, chat?
So, okay, what are we looking at here? Well, we're looking at the plane that has the x-axis 0.2.
Yeah.
At the 0.2 here, and here is outside the plane, and here's inside.
So we're imagining a plane of thickness, whatever, and it's coming out of the screen at us, aren't we?
Yeah. Well, it's 2D.
If we imagine 3D, it's that kind of plane, isn't it? But yeah, it's 2D.
Yeah. This is just a line that goes along the x-axis, and now you can create that. You can flip it 90 degrees. So if you take this line, have float dx, and you create a new line called float dy.
Thanks, Dragon. We're going at the right pace apparently, so that's good.
And that is equal pos y minus pos size y, right?
Let me get.
And you return dy. What happens then?
Yeah.
Got that? Amazing, right?
Yeah.
So we got sort of a sharp edge 90 degrees from each other. So we can put these two together. We take the intersection of these two planes by taking the max function. And we get something, I hope, that looks interesting.
Oh, we got a corner.
We got a corner. And that is step in maybe some kind of right direction, right?
Yeah, a right angle direction.
Yes, right angle direction. So how do we get the other corners? There are different approaches, but one way to do it is to say, one way to do it, this is a very common technique, and we're going to do a domain repetition, it's called. And we're going to repeat this corner 4 times, using a very cheap technique, and hopefully I don't mess this up. And how we do it is quite simple. So I think it's probably maybe easier to do it, and hopefully it looks right, and I don't mess up and I have to look in my pre-planned notes.
You shouldn't have given that away.
Yeah. Boom. And we have a box.
We do indeed.
So what happened there, right? Well, what happened there when we did apps position, to think of it, is that we repeated this shape into the other quadrants. And the way we did it, we took this point here, and it's kind of crazy, but when we this is maybe called a folding operation or whatever, but a little bit hard to imagine. But we fold this point here into this point by taking the apps position here.
Yeah.
This point here becomes this point here, and then we get the same color over here. And this point here gets also mapped into this point here, and it also gets the same color. So we are able to sort of repeat this object and turn it 90 degrees using just a simple apps operation.
That's pretty mind-blowing, I think that's great.
Yes, and we can do many other things for that. But usually I would be thinking, like, I learned all these tricks, and I don't come up with this, but when you are inside this space of distance functions, you would try to find these foldings to sort of fold space into different areas to sort of avoid doing work.
Yeah.
You try to exploit symmetries. Maybe you can say you do the work once and then you exploit it multiple times. And the cool thing about that is, if you show it, this folding operation is kind of for free. So sometimes you can kind of go infinite, and it looks like you created something immensely complicated object, and it kind of breaks your mind try to think how that comes up. But we're actually doing just cleverly folded this object into something that is a fractal shape, and it costs you nothing to do it.
Yeah.
And that's also what I like with shaders, is that sometimes you're able to create these effects that looks so hard to do, but when you look at the source code, they go, oh, I still think it's like I don't get the source code because it just looks too simple.
Yeah, it's too simple. Yeah.
But what we did here, right? If we break this down a little bit again, we created a corner like this. Ah, crap.
I'll do that one.
Whatever. Comment it out. We created a corner. And the way we created the corner, what we created is kind of a plane that went in that direction and a plane that went in that direction. And then we took the union of that, because we have the distance. This is a distance function towards this line or plane.
Yeah.
I say plane, but it's more like line, right? And take the distance function, and then using the distance function, then we get this corner, right? Because that is the intersection between something that goes this way and something that goes this way.
Yes.
And then by using the abs function, we sort of reflect this, or we sort of duplicate this effort into 4 corners and getting it this way for free, kind of.
Amazing.
And this is something, when we start talking about 3D, this is going to happen in 3D as well, but then it's going to be much harder to visualize. So I think this is one of the reasons I wanted to start simple, if you know what I mean.
No, I think it's great, and the way you've done the colours, with the inside and outside, and the fade to black, it really makes it clear that we're talking about distance in a plane here.
Yes, yeah, I think that helps. Let's put them all together now in one big hurrah. So we take the mean function of d1 and d2. If I can just find the correct characters.
Yep.
And we get this one. And now we take the mean again of this box we created, this very nice box. See if that something happens. So if you type mean,
Oops, I'm somewhere else. Where am I? I'll just type that in. There we are. I'm in the right place.
D3. Yeah, comma D3. It doesn't matter.
Okay. I'll do comma D3. Is that what you wanted?
Yeah, and it looks kind of weird, right? But let's start the animation here, right? I click here. So it looks weird, right? But what we're having now is the union of all these shapes, which is kind of cool. And we can also go, I'm going to change this, max. So then we subtracted this box from these things here. And we just did it, just so simple, I think.
Yeah.
The kind of
and you
operations we do to sort of create something. I mean, it's not that cool looking, but it's a quite sort of, well, it kind of looked like back here. I thought it looks like almost like a tool or a logo. This could be
this could be a logo. Yeah, it could be.
Yeah. Logo for whatever, right? And we built it using simple mathematical sort of functions. Let's see now. What shall we do next? But let's talk about what we've done. I like to do that sometimes. So we created this code here. That d is distance to the object, and now the object is much more complex than a circle. It's something else.
Yeah.
And then we made this helper function down here, a code that we, basically, if the distance is less than 0.2, it becomes white, and that is the whiteboard we see here. But in order to sort of be able to sort of visualize the distance field more easily, we also take the distance modulus 0.1 to sort of be, and that repeats like this. But in order to sort of, fade it out, this first repetition is 1, this is 2, this is 3. So then we compute ND. And then what we do in here is that we just take the red color, if inside, divided by this ND and sort of by ND. So it's very simple stuff, I would argue. Maybe it's easy for me to say, but I think it's not mind-blowing hard. The real benefit is that this is applied. We are in a quite pure mathematical world, and this is applied for each pixel. Try to imagine how to draw this thing in a canvas.
You couldn't. That's what I was saying. You couldn't imagine how even to begin it, let alone code the animation, the rotation round. But say what you're doing here is just saying, apply this one function, or this what we've got here, this main method. Apply that to every pixel on the canvas, and it just kind of works because it's all being done in this massively parallel fashion.
Yes,
you've got thousands of thousands, tens of thousands of shader cores that are doing this.
And then something that looks, I mean, it doesn't look super advanced, but if you had this other, if you would be in this model of thinking canvas, or like I'm drawing a rectangle, I'm drawing circles, like these primitives, we normally work on, then understanding how you do these things here is like, I would be thinking about, taking intersections of triangles, and that's very, very complicated, and then I get tired. But here it's like, this wasn't so hard, because we have a kind of completely different framework to deal with shapes, causing the distance fields. And I love these distance fields. I don't want to do triangles anymore. I'm sick of them. Everything should be distance fields. If it cannot be expressed as distance field, it's not worth doing.
It's really interesting actually, because there's a tutorial series on OpenGL, which I've got a link to on Edge on there, and it's just obsessed with triangles. So yeah.
Yeah. Because that's how games works, right? They talk about triangles. And I'm like, triangles are complicated. It's hard. It's hard stuff to do it. I think, at least. Maybe I'm not have the right tools. Maybe there's different tool set. Here it's just simple stuff. It's just distances, and you create these things, and it looks cool. Shall we try to do some cool, a little bit more advanced? Like try to create a kaleidoscope. If you know how
kaleidoscope. Yes, that'd be good. Yes, yeah. It can be psychedelic.
So the way we do how would you do a kaleidoscope?
Do we want to save this program off somewhere? Are we going to
save it for.
I'll save this for we'll put it.
But we're going to continue work on this thing.
Yeah, I'll save it
as a shader one. Codebase Alpha 1.
There we go. So that'll be up on GitHub at the end of the stream.
Yes. So what we're going to do now here is, in order to do a kaleidoscope, what we want to do is something quite similar to what we did, where we map. We have a pixel here, and we map it into, like, you remember the apps function, right? We had here. What we did is, like, maybe let's make the graphics a little bit more simple, so it's easier to sort of think and talk about. So we just type D3. No, D3. So the thing we did here, the magic here, right?
Yeah.
And I typed the comment thing again because I don't know where the comments are. I haven't learned it yet.
There we go.
So what we did here was this thing that when adding this apps function here, we made this pixel here actually mapped into this quadrant. So there is a quadrant here, right?
Yeah.
Where these positions are all positive, and this one is negative, and all these are negative. So the apps function maps all these into one quadrant, and then we compute the color, and then we can get the repetition. In order to do a kaleidoscope, we want to do that like for maybe every 30 degrees. And the point there is the same, that we try to sort of map, with a kaleidoscope, we try to map these points that are outside this angle. I'm trying to draw an angle here, sorry.
Mm-hmm.
We try to map all of these points inside here and sort of, do the logic. And how are we going to do that? Well, now what we're going to do then is we're going to map the positions into the polar coordinate system, if that rings a bell.
Yep.
Do operations in a polar coordinate system, and then map it back to the rectangular coordinate system. Because when we're in the polar coordinate system, these kind of operations are simple to do.
Yeah.
So this is what you try to do as again with shader. You try to sort of, if something is complicated in some domain, let's change the other domain where it's simple, and do it that way.
So just to kind of summarize, polar coordinates mean it's an angle and a length.
Yes.
So it's rather than describing a vector as being point x, y, it's an angle from the x-axis, for example, in the 2D plane, and then a distance from the origin or from wherever we're measuring from. Yeah.
But I would suggest that in order to make this a little bit easier to work with, we're going to break out all this distance function into a helper function. And I usually call it df, that is just distance function. So if you make a new function, you can call it whatever you want. I just call it df for distance function.
Is it a float?
Put it below the box. I'm going to grab some water. That's good. And at the input, it takes a position, a vector. And here you just copy paste this float D1, float D3, these lines, and you move it up there.
Well, sorry. These lines here.
Yeah, D1, D2, and D3. Yeah, take the D line as well. And then you return D. And you replace UB with POS.
Okay.
And then you call instead of d equals d3, you actually call this function float d equals df ub, and yeah, float d. You forgot the
Sorry,
d.
is that the d? There we go.
I'm going to try something.
Okay.
Someone in chat said to try. Nah, didn't work. Sorry. No, I'm in the wrong keyboard again. I'll switch back. Okay. Make another try. Maybe it works. No.
Oh, there you go.
Yeah, I have the division sign. Thanks.
We'll get there in the end.
Yeah. Anyway, so let's implement a function that maps a rectangular coordinate into a polar coordinate, and let's call it maybe 2 polar, and put it above df. So vec2, it should return right.
Yeah.
2 polar coordinates. Or just 2 polar. You call it whatever you want.
Yeah, that'll be fine.
As the input, it takes a position right. Vec2, rect, or whatever you want to call it. And it should return a vec2, right? Yeah, you need to say vec2. It's not that smart. So what is the x coordinate? That should be the length of this polar coordinate, right?
Yeah.
So that's easy.
Yeah. Yeah.
Oh, the length.
Oh, the length, sorry, yeah.
And the way we compute angle in these situations is usually the arc tangents function, right? And it's called A10.
Yeah.
And y, the erect chord, y is the first part here. That is, it's, y divided by x is how it usually is. And that is how it is. Comma, no, not division, comma, records x. The good thing about we passing the 2 parameters is that now it's actually, because usually there is a,
oh, I see, right, yeah, okay.
You have to sort of figure out which quadrant it lies in, but this way it actually solves that problem for us. So it actually returns the right angle. And then we need to do a function that actually goes other direction, right? Takes we go 2 vector coordinates. And what does that return? It returns a vec2, obviously. But the x vector is then, polar coordinates. The x-axis is the length, and then we multiply the length by cosine of the,
right, yeah.
Not length, but the polar chords.
Oh yes, the very first, the x, yeah, the top,
yes.
The first one. So that'll be polar chords dot x.
Yes.
Times
multiply
sine.
Cosine.
You're right, it's cosine of the angle, which is
polar chords y.
Yeah.
Back to school now.
Yeah, it's trying to remember all this stuff is.
This was some years ago for you and for me.
It was a long time for me.
Polar chords x. But this is also what I like about this thing here. when people talk about, math. Well, we can do ray tracers with math. That's pretty cool, I don't know about all this other calculus stuff, but at least linear algebra and cosine and sine, we can do sound, we can do ray tracers. That's good stuff.
Isn't it the angle though?
Yes.
It's y, isn't it?
You're correct.
And then we can do the same with the
What's
sine.
nice about this is, even if you mess up, usually things it looks wrong, but it looks cool.
Yeah.
You remember when we did this? I tried to make it the ellipse into a circle.
Yeah.
I completely failed, but it still looked wow.
Yeah, it looked good.
Cool, right? It didn't crash. So now in df function now, right? We're going to convert this position into a polar position, whatever, right?
Mm-hmm.
So at top of this float df.
Okay. So
it's a new vec2, right? And I don't know, it's called a p-pos or whatever, or polar, or yeah, you call it whatever you want. 2 polar coordinates. And you take the pos. And if we haven't messed up, if we then say pos is equal to 2 rectangular, right, next line, it should be the same, because they should be it should be the inversion, right? And they should, nothing should happen here except we wasted a few clock cycles.
Yep, so that should be the same.
And it looks the same, right?
It does look the same, yeah.
Yeah. So let's. I'm gonna make some small modifications here, and so I'm gonna remove these. We don't need them for now. I'm just gonna offset this thing here. Did I make a mistake? Oh yeah, I messed up somehow. Now I find division sign, but I didn't want it. How ironic. What I want to do now when we're going to try to do this kaleidoscope is I want to offset this from Origo. So we're going to apply some kind of rotation here. So now yeah. But so one thing you can do now is what happens if you take the p-pos and you just add a number to the y coordinates, just like 1?
We'll do down here.
You do it before you transfer back to rectangular coordinates. So we try to sort of see what happens when we make some modifications to see if this actually worked correctly.
So to the y, for example.
Yes, and you just take +1 or whatever.
Here we are.
Okay. Something happened.
Something certainly happened.
And if you take -1, what happens then?
Okay, so we are reflecting it around, aren't we? And rotating and reflecting both of it.
Yes, we're basically kind of applying kind of a global rotation to the object, right?
Yeah.
If you want to try something weird, take plus pos x. That's going to look weird.
Oh wow.
So what we do now is, depending on what the x coordinate is, we rotate the object differently. So we distort the space. This is a very weird transformation, but it looks, oh well, this is a bit cool, I think.
Once again, it's a logo in the making, isn't it? You can see someone having it.
So that's when I wanted to do it. But basically, depending where we are on the x, so what you can do now, there are many different ways, but depending on what the input x coordinate are of the pixel, we rotate it differently.
Yeah.
So that's what creates this distortion. So this is just one way where you sort of, you try things and, oh, this looks cool, keep it. And once again, because this is distance functions, it's actually quite robust for these kind of changes. So it looks okay-ish, even if you do kind of weird stuff like this, which has no real meaning. Now, also try to modify the x, because that is the... So let's multiply that by 1 to start with, just to sort of see what happens. There should be nothing, like. But what happens if you multiply by 2?
Okay, we shrunk it.
We shrunk it, right? So because we are sort of modifying the radius of the thing. So once again, we can go weird here, and then you take plus pos y. 2 plus pos y. No, not p pos, pos. Okay. If you change that to 1 instead of plus 2.
Oh, wow.
Yeah, so well, you go like, what? What is this? But it's, you distort. Basically, what you've done is kind of distorted space now in a weird way. I can write this as well. See what happens. I'm just to do something here. I'm not sure this is the right place to put it.
Oh, very good.
Yeah, so we kind of we kind of reflected this and distorted it. So we're doing weird stuff now.
So that pos thing's very good. It's reflecting it, isn't it? So that's interesting.
Yes. But we wanted to do a kaleidoscope, right?
Yeah.
So let's remove this cool stuff. We can keep that for now, just to keep in mind that there are some cool stuff too. So I think making kaleidoscope is much simpler than you might think. I think this is how you do it. I say mod p. Hopefully I'm not too cocky here and I messed this up, right? I said this was simple. Yeah, I will probably also do a bit cocky, right? No. It's because of the plus sign. Well, no, yeah, okay, sorry. Have to check my notes. Sorry.
Okay. Right.
Yeah. Okay, this is not okay. I get it. I'm going to define.
You want a hash there, don't you?
Yeah, with a hash. Yeah.
So I'll put a hash in for you. There you go.
And then I'm gonna. We all love this one, right?
Oh, we want pi. Okay. Keep
I
going.
believe this is roughly right. And then I need another pound. And then we have the tau, which some people swear by, but I'm not. I just think tau is useful. I'm not sort of, religious about it. Times pi. Sorry.
It's okay. I've got my finger on the escape key to get rid of that. There's something a bit weird with the interaction there, goes, and it brings up my.
Yeah. When I think about it, this is quite obvious.
Ooh.
So now we have kind of repeated the object 6 times, like a kaleidoscope.
Yeah.
And we can even make it 16 times. We only see part of the object, right? But,
yeah.
But what we did here, right? Because we was in this polar coordinate system. We are in a polar coordinate system. And we have the angle, which is the angle of we get the angle of the point. So the angle is maybe 0 here, and by taking the modulus operation, we map the angle in here and in here and in here to create this this sort of kaleidoscopic image, which I think is once again also quite simple once you get it right. So let's see now what we can do. We can. What should we do? Let's. I'm gonna try something here. Okay, by you. Yeah. So now we sort of fit this thing inside each. It's sort of. So let's see what we can do from now. But you get how this kind of kaleidoscopic things work.
Yeah,
right?
yeah, absolutely, yeah.
Yeah. So quite simple math. There's also another quite powerful technique called domain repetition. We talked about that already, but I'm going to write this. I didn't come up with this function. I stole it from a very good site. I'm going to share that site with you, so we can look at this site, which I think is it's a site which contains many cool helper functions that is very useful for a shader programmer. Not all of these are so hard to come up with, but some of these are hard to come up with. So I shared a site here in code share with you.
Okay, there we go.
If you scroll down here a little bit here. So this is primarily designed for sort of 3D shaders, but this is actually a function we can use. So you see they have pictures that demonstrate, if you scroll down even further, how to take unions. So this is quite interesting, how to sort of make soft unions of shapes. So here we can actually use this also in 2D, but we can sort of take soft, instead of taking sharp unions, we can take soft unions.
Yeah.
And we can make this kind of this stepping function. So it's a really very useful site for this thing, and you sort of copy paste this thing. But we're going to make something quite simple, and that is just doing some simple domain repetition. So if you scroll down here a little bit further, you can see some more interesting examples.
Yeah, so we're starting getting like terrain features. Oh, this is interesting, isn't it? Here.
Also, I want to point out what you're seeing here on the bottom. Actually, this shape here.
There's distance functions, isn't it?
That is the distance to this object from here.
Mm-hmm.
Actually seeing the distance function, but that is just. But they cannot see the distance function for the 3D. But what they've done is they take a sort of I don't know what the right word for that is, but they took the intersection kind of a plane, and you can see the distance function like water.
Yeah.
Kind of. But it is actually a distance function from this object. So yeah, scroll down further. I think I lost the focus.
Easy to do.
But here are some very useful things where we're repeating objects over and over again. And that's very useful. So we're going to steal one of these functions. I think it's called pmod2, the one I want to steal. Yeah, there are lots of them. If you search for pmod or fmod, perhaps it is something like that. Yeah, search for mod 2.
God, I don't know how to search. Find on page. What is it? Pmod? Pmod 2?
Mod 2.
Mod 2.
And again. So we find the definition.
There we go.
So you basically take this function and copy paste it. This is what we do here. Now, yes. Oh, now we see some new. Put it above the df function as well. So now we see a new feature here, which is sometimes used, and that is the in-out. You can actually specify in-out parameters.
Okay, right, yeah.
Yeah, but I mean, as a C# developer, this is not so mind-blowing, right? It basically means a ref parameter.
Yeah, pretty straightforward.
Yeah. So let's use this one. I'm going to comment out here this. No, but I learned.
Yeah, you
now.
did it.
Hooray! Let's try to repeat this thing here. So what we do now is I say p mod 2 pass back to like that. So what we're looking at now here is that once again we're kind of doing this. What should you say? We are mapping this point into
to different places. Yeah.
Yes, using these model operations. And now when I comment this, remove this comment out here.
There we go.
Now it looks a little bit, different.
Chaotic, yeah. But it's still a very interesting kind of shape, isn't it?
Yes. If you comment this thing out here.
Which one? The pmod?
Yeah, pmod here. No, not comment it out, but you take that, right?
Copy it, yeah.
Yeah, copy it, and you put it below post rect, maybe. See what happens, because the ordering how we do these things it matters. Yeah, this is more how I envision it to look, right? Yes, I hope so. I experiment with this thing here. Well, things are starting to happen here, right?
They certainly are.
This is a space where this is repeated, and then we have this sort of kaleidoscopic shape of it. And we can also do weird stuff. Let's do weird stuff, right?
Yeah, we like weird stuff. This is Codebase Alpha. We do weird stuff all the time.
Yes, and now this. No. How we do that thing? Wow, doesn't matter. I tried. It was when I thought about it. Still, but we have created kind of kaleidoscope. It's not super cool, but we're getting there, right?
Absolutely.
We're repeating things. What do you think are the next steps here? What do you want to do?
Can we make the whole thing rotate? Can we do that?
Of course. Yes. So how do we want to make it rotate?
Well, we need to introduce time into it, don't we?
Yeah. I think we could just add this p pos y if you just add the time to it. So
this value
below p pos y.
Yeah. Plus equals time, yeah.
Yes, something like that. See how it looks. I have no idea what happened. Press play.
It certainly rotates.
And it looks quite cool, actually.
Yeah, it's very much a kaleidoscope now.
I'm gonna watch your stream now because it's better frame rate. Yeah. It actually looks. This is not too bad. I think we've done a good job already.
It's pretty good.
Yeah. So.
Well, if we increase the number of, I wonder if we could reduce it, perhaps.
So if we make what we can do now is if we make because how kaleidoscope works is like you have this simple stuff, and then because of this repetition, it gets this quite interesting aesthetics, right?
Mm.
But we have this very simple pattern, So if you make the pattern a little bit more complicated by sort of, taking a circle perhaps, or these other things we did before, and we make the pattern more complex, I think we can make our kaleidoscope more complex.
Yeah,
right?
That sounds good.
So let's say you make a float D1 here.
Where do you want me to make that?
You have the float D3, and maybe add float D1. And you add a circle perhaps, or whatever, or the softbox here, and just see what happens. We can remove this kaleidoscope thing, right? By you just comment out the mod thing up there, row 71. At least, it doesn't, because you have to make the program, and then you write the circle.
Oh yeah.
The circle pass 0.1 perhaps, or 0. Sorry. Yes, and then you take perhaps the union of these two, the mean function.
With D1 and D3, yeah.
Yeah, mean D1, D3, for example.
Oh yeah, that's looking cool. Looking cool, that.
Okay, let's see how that looks if we make that into, if you uncomment this kaleidoscopic thing, right? And then you start the rotation here. Yeah, okay, well. I mean, once you come back to this thing, if you didn't know how to do this, kind of, how would you?
I wouldn't know where to start. You wouldn't know where
Yes.
to start. You'd have no idea.
I think what's missing here, and this is something I put in some effort. This is complicated. So we want. I think something that's missing here is, like, if you look at the corner here, or at the line here, we can see the line because the object is kind of, it's not reflected. In a kaleidoscope, you would assume that the shape would be reflected, and we can get that working, because what we're going to do now is going to reverse how it's reflected here. But getting that right, I did it before the stream, right? Sorry, I'm switching your screen. Sorry. Getting that right took some time, so I think I'm just going to find that code and share that with you, and because I was struggling with that part. It's not like it's so hard when you do it, but it's just finding the right permutation of code. Like, I had to start thinking, and I don't like that. I get angry. Let's see now. What did I do here? Okay. I'm going to share with you the rough structure I did here, and then we can sort of think with it.
Okay. You're putting that into code share?
Yes.
Okay.
How my code looked, and we see if that thing works. I'm getting it. Now it's in code share.
Lovely.
You see, I had a little bit different names, and
yeah, we'll sort that out.
But we just make them.
Where would you like to drop that?
I'm going to open it. So drop that. Make that in a new function, and we tinker till it to it compile, right? So just make a new function, df2 perhaps.
Is it a float?
Yeah, float. Yeah. df2. My great naming things comes up again. And you just return 0 from this function. So you see, I had a two polar. Mine was called two polar. So you say two polar corners, right? And it should say pos instead of p. And instead of 64, let's say what do we have? 6. Because this is how many times it repeated, and then we have np. The point here is that you see what this thing is doing is it tries to reverse the angle depending on modulus 2. It's a little bit, and in order to get that all right, it's just not very fun. This seems to work. after I've done it, remove this part here. This
one here.
Yeah. And what is it? Oh, and then we say pos here instead of.
Okay. And we want to return
so that
pos.
should work. That should work, I think.
We're
so
returning 0 at the moment. Do you want to return pos?
Sorry?
We're returning 0. Is that correct?
Yeah. What you should do instead now, let's say you copy paste this code here down to there, up there, right?
This code here. So you
not all, but the pmod part to the return.
You want to replace D with that, yeah?
No. You take this pmod and return.
Return pmod, yeah. Oops.
Not sure what happened there. Can I select?
You can do it, yeah.
Yeah, I can. I can use the menus.
Oh, I see. Right, okay.
And then you say copy this part here.
Oh, right. I'll get you.
Yeah. And how does that look if you put that into if you call df2 instead of df? My amazing naming standard.
Where are we calling df? There we are, yeah. df2.
Okay, let's add this what's called this. It looks like the discontinuous, like it's gone.
Yes.
So let's add this part that we didn't have, like plus this time. So after all this, just before we transfer back to rectangular coordinates, you add the time part.
That's right, yeah. I'm trying to spot where it goes here.
Yes. So ppy plus time. And then you play it and we see what happens. I guess something will happen.
There it is. It's doing what you expected. It's doing what a kaleidoscope does, isn't it?
Yeah, it was simple now, right? But it took me some time getting there. Let's change this to 9. And so that's a little bit more like a kaleidoscope is working, right? Am I right?
Yes, it's very much like a. Oh! What did you do there?
Yeah, I changed it to 90, so now we have.
That's even better.
Yeah, so it looks.
That's an acid dream, that is.
But this is, once again, we have just what we've done here is we have worked with this. What you're looking at again is the distance to this object when we're kind of mapping it to. But we are sort of doing these kind of domain repetitions and sort of folding the space and these kind of things, and we're creating this kind of quite complex shape. Like once again, if I was thinking in triangles and all these kind of things, I would be very, very confused on how to do this.
No, you wouldn't be able to do it then. I'm sure you can do it, but I wouldn't.
Yeah. But we would spend more than 2 hours.
Oh, absolutely, yeah. To got this far in 2 hours from just drawing a filled-in circle is amazing.
Yes. So and the base function is not so hard. So I think it's pretty good. Shall we? Before we call the night or whatever, right? Shall we apply some post-processing?
Yes, absolutely.
This is also a very common technique that we do. So now the post-processing technique is like kind of like we want to apply some global in coloring to this scheme. So we have computed the shape, but depending on where we are on the screen, we're going to apply some global color scheme. This is a very common technique to sort of improve the looks or the perceived. This looks like a nice little flower, actually.
It does, yes. It's sort of Indian, actually. It looks Indian design.
We should have some Goa music now and take some drugs.
Yeah, it's like an acid dream, as I say. It's very psychedelic. I'm seeing like, I don't know, weird gingerbread man with glowing eyes kind of circling around it. It's very strange.
It's weird, right?
Yeah.
So, but
it's like the 60s again. Yes, absolutely.
We haven't really broke our backs either, right? With the terms of code we've written. We're sitting here dealing with kind of math and folding space, and sounds kind of hippie as well.
Yeah.
So let's try to do this post-processing. So what I want to do now is that you create a function called and add it before the main function, but after the df function.
Okay.
And I'm going to find a bit of inspiration on how to write it. And the post-process function are going to accept a vector 3, which is the color, and a vector 2, which is the position of on the screen, and it's going to return a new color. So I'm going to look at your screen now. Yes, post-process. Tertiary 3. And you can just start by returning the color, because that is the simplest post-processing. And then you go down and at the bottom, and you call the post-processing function when calling in here vec4. So you pass in the color post-process, all right, exactly right, and color, and the UV position. And you need the 2 S's. Nothing happened because that's what we kind of suspected.
Yeah.
Now, switch the screen here. Now, cool things you can do with colors. You can do very cool things with these colors and sort of get these effects that are, in my opinion, quite simple and still quite interesting. So you can sort of saturate the color. You can make the color more white, kind of.
Okay.
And one very simple way to do that is if I can just find the parentheses. You can take the square root. And what the square root will do is that it will make the values go towards 1, right? When you take the square root of 0.5, it goes 0.7, right?
Yeah.
And so on. So the values goes towards 1. And that means that they becomes more and more what's called saturated. Desaturated is the term I was looking for. So we can say okay. It's hard when there is a little bit of lag. So I'm not sure if it's possible to see that, but oh yeah, we probably can do that. Sorry, call equal clamp call 0.1. Is that how you type it? I was expecting to go more whitish. What happens if I type like that? Return power call. What am I doing wrong?
Don't know. Doesn't seem to have any effect.
Well, it has some kind of effect, but not what I'm
very subtle, isn't it?
What I'm hoping for. It only seems to sort of adjust the brightness, not the. No. Okay, I get it now. I get it. Yeah. If you take the square root of 0, it's still 0. No matter how many square roots you take. Right?
Yeah.
So we can fix that by saying
Oh, there we go. Yeah.
so now you're getting there, right? So because the other components were kind of 0, they remain 0.
Yeah.
But now when we go, now they become more white, right?
Yeah.
When we do this thing, because we are sort of desaturating, and we can also kind of go the opposite direction. We can sort of say we can saturate, make them more intense colors. Now they might be quite intense already, but
I think something's happened to your mic there, Mårten.
sorry, I keep my that. So I think that's pretty interesting with colors. Can you hear me now?
Yes, fine.
Yeah, that by just using the square root and power, we can sort of saturate and desaturate the colors.
Yeah.
And do things with that. So what should we do with this thing here? What kind of post-processing should we do? Well, one post-processing we could do, just to sort of tinker with it, we could sort of make the colors more, let's say more desaturated near the center, right?
Yeah.
And make them more saturated
At the edges.
Yeah, as it goes to the corner. And how do you do that? Well, it's quite simple, because we just take the length of the position,
right,
and pass that length as instead of 9, you said length pass.
Yep, okay, I get that.
You can see what happens. This is just randomization. See how it turns out. So
yeah, certainly see that.
Yeah. Now in the middle of the screen, it's desaturated, and at the corner, and then the further you go out, it gets more and more saturated. So it creates, I think, using this very, very simple technique, we introduce a little bit more. Yeah, it makes more a gradient in the shape and make it look slightly more interesting, I think.
And
that is kind of purpose of this post processing, that you sort of apply this kind of sort of simple cheating post processing to make it looks a little bit more appealing. And this was not very complicated, right?
No, let's try and reversing that. Should we try putting it so that it gets brighter at the edges?
Yeah.
It's not quite so noticeable, but
you can always take you can always just tweak by
just play around with it. Yeah,
taking 2 or 0.5, and they're always possible to sort of tweak the numbers a little bit.
Yeah, I think we'll put it back to that because it's noticeable that way.
Yeah.
Yeah, cool.
And so that's one way to do it. There's something else we should do, perhaps, on the post processing. Maybe we should change the colors as well, sort of.
Oh yes, that'd be good. Kaleidoscopes often do that as well, don't they? They have to vary the color.
Yeah. Let's think a little bit how we do that. Well, one way to do it, which is just pure cheating, and sort of no science at all behind it. Let's see what happens. That is how I operate when I write shaders. I try things and see if I like it, and if I like it, I declare myself being a genius and move on.
And you forget about it if it's horrible. Yeah.
And if it doesn't look good, I don't care for it. So So this is just randomized coding.
Ooh.
Let's see if that's it looks. But now we see the colors change a little bit over the screen, right?
Yeah, there's definitely color variation. Yeah.
The only thing I did was change the saturation of the red and the blue depending on depending on X and Y. It's not really it's nothing brilliant, but we got a little bit this kind of effect of it, right? Let's implement the rotation function that allows us to rotate the coordinate, and that's quite simple to do. So make a function called above post process, and we call it rotate or whatever. It doesn't matter, and it returns void, and it takes an in-out parameter, which is a vec2, and p pos. Pos or whatever you want to call it. I said p-pos, I meant pos, but it doesn't matter.
I'll change the pos.
Whatever you're happy with.
Yeah.
And comma and a comma and an angle. Bloom effect, yeah. Dragon eye. And now we're going to rotate this position. And perhaps I just type how I do
you carry on, yeah.
So what I do is I compute the cosine, because I'm not sure this is a smart thing to do, but this is just how I usually do it.
Yeah, just do it.
Float S angle, and then we take pos equal vec2 cosine times p pos dot x plus no, what is the plus sign?
Yeah, the plus. There you
go. Pos dot y comma. I have a memory rule for this one as well, which is not like this. What you said was x y.
X y z z y, yeah.
Yeah. Hard. Pos dot x, and can we have a plus again?
There you go.
Multiply by pos y. No?
There you go.
Yes. And then I'm just going to rotate. What was the function called? Rotate?
Rotate, yeah.
Pos by time.
Wow.
See what happens. I think we can see then that the idea is that colors then rotate around.
That's really like a kaleidoscope now with the colours changing, yeah. It's amazing.
So once again, it's not really we broke our back writing these graphics, but it's still pretty. I think it's pretty cool.
Absolutely, yeah. I also like the way that you can experiment. It's very similar to what we were doing with the T4 templates. You write a little bit and then you just kind of mess around, and you say using very simple mathematical functions, so that there's your vector maths, using absolute values or modulus, and then using just simple trig functions like sine and cosine.
Yeah.
And you can just mix and match and play, can't you? I mean, we could do. There's many things you could do in there. just to try.
And what we're looking at again is the distance function. We're like, and once again, this is what I like about the distance function, because they're so, I found it so quite robust to combine. It's quite hard. It's quite simple to predict the results. It's conceptually quite simple to understand, I think, what the distance function is, and it's quite simple to sort of, do interesting things with it, I think.
Yeah, absolutely.
So I think maybe we're coming to a point where it's good to sort of round off. Do you agree?
Absolutely. What we'll do is we'll save this file so that folks can get hold of a copy of it.
Yeah, I think you should share. But I really recommend anyone sort of interested in trying this thing is to go to the Shady Toy site. I think that's a very cool site. And right now the Shady Toy site will be seen a little bit overwhelming, but I hope that maybe next time or next time after that, depending on how we pace this thing, we're going to talk about how we can sort of understand how a 3D ray marcher work.
Yeah.
And then it will be possible to understand. But also, I really recommend the Kodelife editor. I think this is a really nice editor to work with. Hope you agree.
I think it's the immediate results, isn't it? We haven't got to mess around with writing a C++ program. We haven't got to compile anything. We haven't got to do makes. We haven't got to worry about include files. It's all just there for us, isn't it? It's very simple to play with.
Good, Dragon. I hope you feel better. I have headaches from time to time, and I know it's not good, but I hope you feel better.
Yes, it is one of those kind of things where it's like a 19. Do you remember The Man from U.N.C.L.E. and things like those spy films where they used to hypnotize people with things like this, the hypnosis machine.
Yeah. Yes.
It's a bit like that.
So ray marchers but I think Kodelife is really nice to work with. And like I said, we haven't compiled. We just writing code, and what's nice is it very seldomly crash. So even though you write something strange, it might look weird, but sometimes weird is what you're looking for. This looks weird. I keep it. I don't really understand it. And I also think when we go forward to the ray marchers, I think understanding the distance functions, how the concept of them, that we are seeing an object, but the object is the function. What the function gives us is the distance to the function, to the object, kind of to the surface of the object. And with 2D, using these helper functions, you remember these gradients we have, or like this that went out, the simple things, right? Now it's hard to see, but in the beginning it was quite simple to see. I think it's easy to understand how a distance function or distance field work. But we're gonna generalize that into 3D, and we're gonna use this distance field to. What we're going to do in 3D is we're going to start. Let's imagine this was a simple object, but we're going to start at a point, and we're going to traverse along a ray here. And let's say we want to intersect this point here. So then we're going to ask the distance function, what is the closest point to the surface from this point where I'm currently at? And then it might just say this distance, which is 1. And then we're going to, but we are marching in this direction. So the closest point is this, so we march that distance, okay? But we missed it. So then we ask again, now this is the distance. And then we march that distance again, and then we get an intersection. And that is basically how ray marcher works, is that we ask how far is it to the object, and then we go that distance towards the object and see if we get an intersection. And if you get an intersection, then we are hit the surface, and from that we can compute the normal using the distance function. I'm going to show you how to do that. It's not so complicated. But then we can compute the normal, and when we have the normal, we can compute the shading,
reflections,
and reflections, and all these kind of things, and then we're basically done, kind of, right? So it's but understanding kind of how the distance field work, which I hope to achieve a little bit with these 2D things, I think will help to understand the 3D ray marchers as well.
Yeah, I think you've really explained it really well. And as we've gone through the kind of 2.5 hours, we started, as you say, start off with a circle, then draw circles around it for the distance it really kind of brings it home. And then when you get to this point, the kind of distance function is almost kind of in the background, isn't it? We're actually now starting to play with reflections and you gave it a name, domain
repetition.
Repetition, that's right. Yeah.
But it is really that distance function. But we're going to do the same things with 3D. If you have a shape, a sphere in 3D is just a circle in 2D.
That's right. Yeah.
And we can create this box in the same principle as we did in 2D. But we have to do 3 planes and intersect, right? And then we can do this min max function to sort of make them to find the
combinations or the
intersections and create complex objects and complex fractals. And then of course these kind of cool smoothing functions where you have the mean function, which is like a smoothing function, and we can create these smooth intersections. But it basically comes down to the distance function and different ways to sort of combine it. So, and also this domain repetition. So I think 2D is a good way to start.
This is, I mean, what you've done this evening, Mårten, is it's kind of blown the water out of the tutorial I was reading, which was very much around building triangles, and I guess that's if you're doing computer games, you're building your 3D models out of triangles, but this is a much more immediate way into the GLSL and more, you get instant gratification, really, don't you? You're getting nice results straight away.
Yeah, and we could actually make this what we've done here. We can try to do it. We can maybe start it with next time. We can sort of make this into a shader toy. Actually, it would be good if we try to make it a shader toy now, but I think we're getting a little bit late. But this is something. Let's try to do it next time, right?
Yeah.
So we make this into a shader toy examples, because that's a cool thing about this thing as well, that we created something here and now we can share it on shader toy and show off our mad skills. Of course, I don't think this will get many upvotes because they are crazy at shader toy, but I mean, we can show our co-workers, look at this, so I've done. And so that we should try to do that next time.
Yeah, we'll advertise the stream a bit on there as well, won't we? So people maybe want to go and shader toy and want to learn a bit about this can at least find this video when it's up on YouTube. So yeah.
Yes. So that's something we shouldn't forget. We can start with that next round if you want to do it and do it with shader. But at least that's kind of what I wanted to tell today.
So it's been fantastic, Mårten. Thank you very much. Thank you everyone who's been in chat and watched. Dragon Eye. I've got a light shining me. I get sub. Thank you for joining and responding in chat. It's been great. Thank you so much, Mårten. I look forward to the next stream, which will be it's subject to planning next Monday if you're available.
Yeah, I think we can do that. Cool. Next week is okay. The next week after that, I'm going away to Barcelona on work trip.
Lucky you.
It's not that fun.
Well, we'll work around obviously your input, and maybe we can get another 3 or 4 streams out of this kind of content, because I think it's really. I mean, the reason why I did audio things is one of the kind of basic things you do when you get a computer and you want to program it is make noises. The other thing is you want to make pictures.
Yeah, I agree.
It's all kind of very it's like that instant reward for doing it. So thanks so much.
And also, I want to touch on that. What you said is like what I started with when I started many years ago. Is like I want to do cool graphics.
Yeah.
So I actually think when rediscovering this shader world, I'm going back to my roots and I'm having such a good time.
Yeah. Fantastic. So thanks so much. Let's go and let's call it an evening now, and we'll go and find someone to raid. So thank you so much. Let's go.
No problem.
Over on
Gareth is streaming.
Is it Gareth streaming? Is it? We'll go and raid Gareth then. So he is. Yeah, we'll go and join Gareth. So do stay with me for the raid on Gareth Hubble's stream. He looks like he's on a be back soon at the moment. So just spam his chat with any emotes you have. If you have any of my alpha emotes, do the same. And we'll see you again I'm planning to stream again on Wednesday, where we do a bit more text adventure work. So we'll see you then. So take care, everybody. Enjoy the raid.